Welcome to SDC2020. My name is Doug Dumitru. I am the CTO of WildFire Storage. I have been involved in all-flash storage since about 2007. Today, we will be talking about techniques to improve the value and performance of flash storage using fine-grained block translation. First, some notes from our lawyers. The first question about block translation should be, why bother doing it at all? After all, current SSDs have really good FTLs. The truth is that you can accomplish more on the host than any SSD can do on the device, no matter how good the FTL is. The host just has more resources, and more importantly, it sees all of the data, not just what one drive sees. Block translation can lower flash wear and at the same time improve performance. More importantly, block translation can reduce storage costs by storing more data on less hardware, and arrays are uniquely impacted. With block translation in place, parity RAID levels like RAID 5 and RAID 6 not only yield more space than mirroring, but actually write much faster. We will discuss how block translation can be implemented with near 100% efficiency in terms of device space and device bandwidth. Block translation can mean a lot of things to different people. A lot of this depends on how dynamic the translation is. This can range from very simple to very complex. The obvious simple place to start is with static layouts. When you create a partition table, you are translating block addresses. This translation is very simple. Just add an offset and check a range. Nothing changes over the lifetime of the live device. Some static translations are more complex. The mapping of RAID 6 reading in degraded mode is still just a static mapping. You might have to do some real compute work, but the blocks are not constantly moving around. As we get into other examples, the blocks do start to move around, but in a limited manner. If a hard drive remaps a bad block, the performance of the remapping is not a big issue. After all, you have just waited for a retry timeout anyway. This lets the remap commit a limited amount of data. The same ideas are true for LVM and resizing a volume live. The mappings can change, but you are allowed to lurch when applying a new configuration. There are also real limits that restrict the new changes to a handful of update rules. One place that gets a little more interesting is snapshots and copy on write. In this case, you are live mapping block updates. The layouts are still kept simple, typically limiting the number of mappable blocks to 64,000 or lower. This keeps the database aspects of LVM manageable. Some solutions actually map dynamically as they run. ZFS is like this with every new update going to a new location. In this case, there's no separate database and the block sizes are large. The issue with ZFS is not the overhead of the remapping, but the overhead of just finding a block. Finally, some storage hardware requires that you map every block. With SSDs and other flash media, the flash itself enforces update rules that basically make the device useless as a standard read-write block device. It is up to the controller's firmware and flash translation layer, or FTL, to map small blocks dynamically to target flash addresses. The FTL layer itself is quite complicated and often does quite unexpected things when running. This is why there's a real push to move the logic out of the FTL to the host. You can also just leave the FTL in place, but feed it a write workload that avoids the FTL's overhead. By writing in big linear chunks, the FTL will no longer need to do garbage collection. This can minimize FTL write amplification while still relying on the SSD controller for important stuff like error correction and wear leveling. Some devices such as SMR hard disks have similar update rules. In the end, if you can update the device in linear chunks, you get closer to the maximum write bandwidth that the device has to offer. So we're going to map blocks on the host. With bigger devices, this becomes a big data set to manage. A 40 terabyte array is 10 billion distinct blocks when cut into 4K pieces. If you cut this into 512 byte pieces, it is 80 billion blocks. This huge number of blocks is why some systems try to deal with much bigger blocks. ZFS likes 128K blocks for dedupe. These blocks are this big because there are fewer of them. We will be dealing with 4K blocks. In terms of a RAM-based map, 4K blocks need about 50 gigabytes of RAM to map an LBA to a target location. 50 gigabytes may not seem like a lot unless you are the one paying for it, or you are a device designer and 2 gigabytes is the upper limit of your controller design. 40 terabytes is also not that big of a device. In 2U with commonly available SSDs, it is easy to get to 150 terabytes. With dense chassis or U2 NVMe drives, 300 terabytes is pretty easy. With the newer ruler-style SSDs, 300 terabytes in 1U is not that hard. The fact that you can build a 300 terabyte 1U flash appliance forgets one important factor. The cost of 300 terabytes of flash is still significant. When building a translation map, we are basically allocating a huge array. Each entry needs to be big enough to target the physical address that the block can reside at. The table itself can be flat memory, virtual memory, a tree of pages, or whatever. Regardless, we need to look up the element and get to the target address very quickly. Fortunately, the allocation is static, so high overhead tools like vmalloc work just fine. In how we pack the data into this array, we can choose performance, space efficiency, or something in between. A 32-bit entry is large enough to map to a 16 terabyte target. So for 40 terabytes, we actually need 34 bits. 8 bytes is tempting for speed, bit packing is tempting for space, and it turns out that a 5-byte table entry is probably a good compromise. So mapping a RAM table is actually pretty easy. The real issue is how to populate the table from the disk when you boot. We actually have a classic database issue. There are two sets of data that need to be kept in sync. When we update some number of data blocks, we have to update the RAM mappings in sync with the blocks. What we need is an atomic update. Atomic updates are simple enough. We have a collection of things. We write to the media in a fashion that allows these collections to be grouped together. If we crash in the middle of an update, we will either read all or none of the things. Thus, the update is atomic or indivisible. There are some standard ways to implement atomic updates to media. The most common is the journal. Journals work, but they have a downside. Most notably, you end up writing everything twice. Another option is to update a new set of data and then update a single block to point to the new data. ZFS works like this, so does NTFS, at least in places, and while this works, this tends to scatter writes on the media in ways that the media does not really like. A final option is what is called generation counters. A generation counter means you include a counter that increments with each new generation of data. The mount process can then tell which copy of a particular piece of data is valid based on which one is newer. Make the generation counter big enough and it will never wrap. So where did this all start? Back in late 2005, I had a database customer that was looking for faster storage. The data set was small, only a couple dozen gigabytes, and Flash looked perfect. Unfortunately, the Flash devices at the time did random updates at about 13 IOPS. In looking at the device, the massive differential between linear and random updates looked like an opportunity. What if we could write linearly and track the updates? The first on-host practical FTL was born. 5 patents and a couple of OEM licenses later, the solution still works and still kicks butt in terms of performance and value. This all works because of the on-disk data layout. This layout implements writes that are friendly to Flash, friendly to RAM usage, friendly to RAID, and still implement atomic writes using updates that rely on generation counters. The updates themselves have very long write stripes. These stripes are large enough to null out the garbage collection of most SSDs. If you have an array, they are large enough to null out the FTLs of the member SSDs in the array. To keep memory reasonable, a mid-size structure is used to actually buffer writes. This buffer size sets the upper limit of how big an atomic update can be. The smallest structure is the actual atomic update segment. The segment looks like a small journal entry, but it is not a journal. It is the live data. The write segment is basically a sandwich with a header and a footer that surround data blocks. The size of the payload is variable, so a single update might represent a single 4K block or many hundreds of blocks. CRCs or hashes are used to verify that the structure is self-consistent. Generation counters tell the mount process which data is newest. This is the layout from 2007. The first cut of this layout tried to maintain 4K alignment on disk. The header is a short structure followed by part of the addressing array. This is then followed by some number of data blocks. There is then one or more footer blocks that finish the addressing array. Because there is a header and footer, it is easy to walk these writes either forward or backward. During mount, if a set of segments just stops, you know you're at the last update that succeeded. So what is in the header? The header itself is quite small. It has a signature so that you can sense old data, perhaps from a previous incarnation of the device. Other than the signature, there are a few count fields, the generation counter, and the data integrity fields. One ideal aspect of this design is that it does not require a one-to-one relationship between mapping elements and data blocks. We call these mapping elements meta tags. This lets you output a meta tag without any associated data block. This is how the device implements trim or discard. A trim is basically a write of an all-zero block. If you actually write an all-zero block, the media will never get the zeros. It just gets a single meta block with some status bits set. For no real reason, we decided to also special case blocks that were all Fs in the same way. Remember that this was done before the trim discard spec was even proposed. Because so little data is written, the inherent speed of a trim or zero write is immensely fast. This can actually be problematic as it fools some benchmarks and produces some impossible performance numbers. This layout shipped on a lot of machines. For mid-sized arrays, it was easily best in class. The one area that was problematic was that it was slow to mount. The mount process would have to walk each segment to read the meta tags that were scattered all over the array. Runtime performance was great though, with over 99% of the device storage surface getting live data blocks. So the first major optimization was to try to make the mount run faster. A side effect of this change also made defrag run faster. Defrag is our name for garbage collection. Some papers also use the term cleaner for the background tasks that move space around. Regardless, in 2007, none of these terms were in use for flash storage. The optimization we came up with was to write a second copy of the meta tag array at the close of every write block. During mount and defrag, we can read this summary array and get all of the mapping for the entire write block without walking each write segment. This works great for all but a single block. The tail end of the write would not have a summary. So on a single block, you still have to walk the segments. But doing this once is far better than doing it tens of thousands of times. This pushes the practical limit of array size to well over 200 terabytes. So now we have an array that reads directly from flash, but writes in long linear swaths. Where does this actually get you? On reads, nothing really changes. You still have to hit the device with physical reads. The LBA lookup process is 1 to 2 memory accesses, which are likely not in cache. Software developers call this a cache line miss. If you're a real software developer, you count cache line misses in your sleep. On writes, things are very different. Because you are writing perfect, linear, aligned writes, you can easily hit the linear write speed of the underlying drives. For 24 drive SATA arrays, this means 11 gigabytes per second for larger blocks and 2+ million IOPS for 4K random writes. One of our licensees coined the phrase, "We write faster than we read." This is still true. All of this does require that the array keep up. We are feeding the array with perfect I/O requests on writes. If your array has 22 plus 2 drives RAID 6 with 32K strikes, the translation layer will always write perfectly aligned 704 kilobyte requests. There are some aspects of RAID that make this easier. First, RAID will never see a read, modify, write operation. Every write is a perfect stripe. Second, you can strip out much of the RAID logic. The entire stripe page cache can be skipped. In the end, you can push your 24 SATA SSDs write speeds to well over 11 gigasecond RAID 6. There is some RAID tweaking, including an internal patch to RAID 5.c. The patch is actually pretty simple and just bypasses a lot of code when writes are perfectly aligned. Remember that with this layer in place, all writes are perfectly aligned all of the time. The first time our testing got above 8 gigabytes per second on writes, the hardware was not really up to it. Flash actually draws more power the faster it is writing. Our early bench systems did not have the power supply capacity to keep the 5-volt rail happy when all of the SSDs suddenly wanted 2.5 amps of juice at the same time. Fortunately, current server systems have solved the 5-volt power distribution issues. This layout is actually really efficient. All blocks maintain alignment on 4K boundaries. Internally, there is only a single data copy of writes from the user space buffer to the outbound buffer. On reads, the read is directly passed to the user space pages. Reads usually do better than a stock array because the small chunk size is better at keeping the array SSDs busy and spreading the workload around. Unlike traditional arrays, very wide arrays are the most efficient option. 24 drive arrays don't need to be striped, and all the drives will wear identically. But 4K aligned blocks are just the beginning. The linear structure of a write segment looks more like a tape stream than a block device. It turns out we can write just about anything on any boundary. Bytes are bytes. So implementing compression is almost trivial. The block has to be compressed, but stock LZ4 can be tuned for 4K blocks and is then good for more than a gigabyte per second per core. So normal hardware is still up to saturating 24 drive arrays with ease, all without any special hardware offloads. The mapping does get a little more granular, so you'll need 6 bytes instead of 5 to support up to 256 terabytes. Above 256 terabytes, you actually have to go to a 7-byte table, but that takes you all the way to 64 petabytes. The write structure is really unchanged, except that the data blocks are packed together on 64-byte boundaries instead of 4K boundaries. For many workloads, you actually get more read and write bandwidth than the device because of the compression ratio. One real issue with compression is that benchmarks can sometimes become difficult to interpret. The payload itself starts to matter more than the I/O pattern. This is not to say that compression has no overhead. It's just that the current hardware can easily keep up. One of the biggest overhead factors is that the blocks are no longer 4K aligned on disk. This becomes an additional memory copy operation. Storage software developers count copy operations even more than they count cache line misses. Fortunately, mainstream servers now have from 4 to 16 DDR4 memory channels, so copies aren't as painful anymore. So now it is time to start thinking outside the box. The atomic write structure is not limited to blocks and meta tags. We can pour whatever data we want into the structure. Our first step, lowering the memory footprint, will store most of the LBA table itself on the disk. This will not only lower memory usage, but also hasten mount times by more than an order of magnitude. It also enables even more fun later on. The first step is to embed most of the LBA table on Flash. Many people have tried swapping big pages to Flash, but this doesn't work. It produces too much write amplification and causes all sorts of edge cage issues, especially with random write workloads. But we can write very small snippets of the LBA table without killing the linear write efficiency of the mapping engine. The atomic write structure actually lends itself very well to writing multiple very small segments. Even writing a 4-entry table gives you a 75% reduction in DRAM usage. Placing the LBA table on Flash using live atomic updates works very well when the extra updates are small relative to the block size being mapped. If you need more than a 75% reduction in DRAM usage, you can actually push a small tree structure to Flash. This can give you a 256x reduction in DRAM usage while only consuming about 2.5% of the Flash capacity, worst case. This represents 100 terabyte devices that can be supported with under a gigabyte of DRAM. Here is a really bad picture of what a 4-level deep on-Flash tree looks like. To look up an LBA, you discard the bottom 8 bits and look up the entry in the in-memory table. Each 2 bits after this is used to reference the entry in the subtable from 0 to 3. After 4 iterations, you have the target address of the data block. Because the data blocks and the microtables are stored in atomic updates, you are guaranteed that the map and the blocks will stay in sync. This saves a lot of RAM. Your base footprint for 40 terabytes goes from 60 gigabytes down to 240 megabytes. Because the subblocks are small, the amount of extra flash used is small. Each subblock is under 24 bytes long, so the worst case overhead for a random byte is under 96 bytes, or about 2.5% of storage. In practice, some of these subblocks are likely overwritten inside of a single atomic update, so the effective extra space is well under 1%. These subblocks can easily be demand paged. Well, perhaps paged is a poor term for this, as 24 bytes is an awfully small page. Regardless, at runtime, the overhead of this layout tends to trend to no extra I/O operations and 4 memory reads or cache line misses. It will take some time for the LBA table to populate from use, but the array will be ready to accept I/O requests very quickly. When you add more stuff to the right atomic segment, you need a bit more in terms of layout. In some ways, this extended layout is actually more logical than the simple version 1 layout. A master header and footer let you walk the segments forward and backward. After the header, you have a list of subheaders that have sizes and counts for each type of object in the right segment. You still have summaries at the end of each write block. Bottom line is that a mount needs to read just a fraction of the array and can run 50x faster. Fast enough to complete inside of a SCSI timeout. This is the requirement to do dual-ported disk HA arrays. So why is low memory so important? Mostly I'm really cheap. I'm also a bit greedy. If I can write software that can save $10 of hardware costs, I can charge $3 for that software really easily. Second, some of the most interesting things with Flash can take a lot of RAM. One example of this is 4K block level dedupe. The problem with dedupe is that if it works, the array can seem utterly massive. 40 terabytes of storage at 10-to-1 data reduction is a 400 terabyte LBA map. The on-demand page subblock mapping segments can keep this RAM growth in check, but still cache very well. LBA tables have a lot of locality of access. The other side of dedupe is the hash block IDs. Block IDs are random because of their hash nature. This means you actually have to have enough RAM for them or be willing to take an extra I/O hit. Most vendors that do dedupe cannot come anywhere near 1 million IOPS, so I suspect that they're taking the I/O hit, or worse. So far, we have just been taking blocks in and putting blocks out on storage. In my software, this has looked like a Windows upper layer filter, a Windows block device, a Linux device mapper target, and now an MQ block device target with a queue request attached. But the layers can be used directly for other stuff. The objects that you're storing don't have the limitations of traditional block storage. They can be variable sized, they can be sparsely mapped. The LBA tables themselves can be used as allocation indicators and even have flags embedded in them. So what else can we do with this? So let's build a file system. This is unlike any file system you've ever seen. There are no pages. Different files are optimized for different types based on their access patterns. Small files are handled in single I/O operations. Bigger files can be objects, logs, or block-based, depending on how they're used. The write structure is still based on the atomic update segment. There is no journal. You can actually get the device bandwidth with operations like small file creates. Plus, as an added benefit, no pages means no allocation units. A file needs space for its contents, its name, and its directory information. There is nothing to pad. Parts of this file system have actually been implemented in Linux under VFS to test. It's not a whole functional system. It only supports a single directory with small files that can be created, read, listed, and deleted. But this is enough to see the possibilities. The underlying storage layer uses a number of block types. Because it is easy to build multiple storage namespaces, we can have separate names for directory control blocks, directory extent lists, groups, file contents, file extent lists, and file random I/O blocks. In extending the definition of a block, there still has to be limits. If we want to map from an 8-byte table, we can actually specify a very wide range of blocks. You have enough room in 8 bytes for 16 petabytes of storage that supports 64 namespaces, variable size blocks from 16 bytes to a megabyte with compression, or up to 64 megabytes without compression. This lets you rethink a lot of the design. Imagine that you can write 7,500 bytes and track it with a single numeric reference with no extra overhead. If your data structure needs 7,500 bytes or 750 kilobytes, you just store it and later reference it with a single operation, and the logic does not add any extra I/O. So building a file system starts to get really interesting. It starts with a directory control block. Directories in a POSIX file system get really hammered. Whenever you update any file, or even read a file, you have to update this one block. This is why the no A time option exists on many mount commands. With this translated structure, you can take this hot data and put it into a tiny block. Because it is tiny, you don't mind writing it a lot. Remember that the write overhead of a map device is based on the write size and not the number of blocks. After the control block, there's a potentially large extents block. This lists the LBAs of the groups that are used to store the directory's files. This is not a simple list of numbers. The LBA structure is thin provision, so you can safely allocate big ranges. So this extents list starts with small block ranges, but grows up to 32K ranges at a single allocate. Storing an array of 32K regions in a 1 megabyte lookup table gives you 128,000 entries of 32K each. This maps to 4 billion groups, or around 40 billion files. And if you need more, adding an additional extension lookup table has almost no overhead. So the limits of directory entries are immense, with very flat performance from small to absolutely huge. So how does a hash directory actually work? The file name is hashed into an 8-byte number. and then you use this number to look up a group directly with a single I/O. But hash lookups usually need to be pre-sized. In this case, we borrow from an open source database from the 1990s, which in turn was inspired by thesis papers from the early 80s. These are dynamic hash routines. This structure lets you start with one group and dynamically grow and shrink to any size while maintaining reasonable balance. The problem with these solutions is they tend to waste space and require a wide range of group sizes at runtime. Mapping all of this to 4K fixed size blocks is a royal pain. But we have variable size blocks, so dynamic arrays just slide right into place. So one memory access away and one I/O away, we have the group with your file. A quick scan of the hash tail gives you the likely exact match without any string operations. Finally, a memory compare verifies you are not dealing with a hash collision. File access both on disk and in memory is lightning fast. Files with small data payloads have the payload stored in group with the directory. This gives you single I/O access to small files with better than database level performance. So how quick and how scalable is this? When running from disk, everything is a single I/O away. Small files are completely contained within their directory entry. Larger files might need an additional read, but the read can be up to a megabyte at a time. Really large files are efficient because their extent count is much lower than traditional page counts. The groups can be split and merged in the background, and each group even has its own local lock, so multi-thread concurrency is really good. Just how good is the performance? Well, we'll get to that in a minute. Again, this is not a typical implementation. There is no page cache. When VFS writes data, the data is queued directly into the atomic write buffer. This structure allows for many updates to become a single write segment without any extra copies. File systems are allowed to delay sync operations, and this design exploits this feature. The lack of a page cache means there are no dirty pages. This does not mean writes are unbuffered, but the buffer is contained within reasonable limits. This smooths out write bandwidth for a better user experience. So how about some numbers? I did some testing on a Core i7 7700K virtual machine with a single SATA SSD. In this setting, VFS has about a 2 microsecond overhead before you even hit the file system logic. For in-ran updates that are small enough to fit inside a single atomic update, file creates come in at under 4 microseconds total. This includes the 2 microseconds of VFS, and this is 4 to 10 times faster than ext4 and 18 to 30 times faster than XFS. It is a whole bunch faster than ZFS, although I didn't measure this. As the directories get bigger, the comparison with other file systems actually get bigger as well. Creating a directory with 4 million files still only took 28 seconds or 7 microseconds per file from a single thread. All of these tests include the sync at the end. This 4 million file test included hundreds of atomic update segments, lots of buffer update merges, and hundreds of thousands of group splits. One reason that this works is that the storage is almost 100% dense data. Very small files store with their directories. There are no allocation units, and big files need fewer extents. In many ways, this is the ideal structure for object storage and key value storage, where files are created and retrieved all at once. It should be obvious that this structure is designed for speed. It gets speed by being efficient at what is stored. Nothing is duplicated. Nothing is padded. Lookups in memory are direct with no complicated algorithms. Even algorithms considered fast, like LBA Trees, are banned because they are too slow. Things like allocation bitmaps are not needed, as the LBA structure itself does double duty. The extra write of journals just doesn't exist. So what are the limits? Many file systems have stupid numbers attached to them as limits. In practice, the limits are actually based on how much time you have to wait. If you want to create 1 billion files, this design keeps up with flash I/O latency of at least 2,500 file creates per second from a single thread. 1 billion files would take about 5 days. This compares to about 20 months for ext4, 6 years for XFS, and I don't want to think about how long it would take ZFS to do this. Again, the limit that matters the most is time. A final benefit is the efficiency of storing small stuff. 1 billion 100-byte files with 20-byte file names will end up occupying about 200 gigabytes of disk. This compares to 5 terabytes for ext4 and XFS. This all works because you have variable size blocks that are translated. To conclude, block translation lets you rethink storage as a collection of objects instead of fixed size blocks. You can build structures that use all of the bandwidth of the backing devices. You get to act like a mad scientist and ignore the conventional design limits. You get to save money by buying less hardware and by having the flash last longer. I hope this gets you to rethink what can actually be done. Thank you very much.